Hello and welcome to Project 152, your weekly specialist exam prep. Now every week we go through past questions from the QCAA. If you stick with us every week, you'll do every question the QCAA has ever done. Now this week we are doing week 22 solutions. These are all tech free. Let's get started. Now with a question like this, we don't have to do any calculations. We just have to know how changing the sample size or changing the confidence level affects our confidence interval. So you can read the question here, but basically it says, assume that the standard deviations for both samples are the same. We're about to take a second sample. The researchers can ensure that a shorter confidence interval width is produced by doing one of these four things. So let's draw in a confidence interval, right? And what's going to happen if I decrease the sample size, right? Now, imagine that you increased the sample size and you increased it so much that you did the entire population. Well, your confidence interval, if you did the entire population, would cease being a confidence interval. You would just know everything about the population. So increasing the sample size squeezes our confidence interval down to a single number, which conversely, if we decrease the sample size, our confidence interval is going to get larger. So that's what happens when you decrease the sample size. So it can't be A or B because we're trying to make our confidence interval smaller. It must be C or D. We need to increase the sample size. Now what about here? Decreasing the confidence interval or increasing the confidence interval? Okay, so if we start here again, if we decrease the confidence interval, right? I don't want to be as certain. At the moment, I'm certain, or I'm, say, 95% certain that it's between here and here. If I only need to be 90% certain, I can shrink it, right? If I only want to be like 50% certain, I can shrink it. If I want to be very, very confident that it's between these two values, then I should increase that. So if I want to shorten it, I need to increase my sample size, right? That'll do that. But I also need to decrease my confidence interval, confidence level. All right, so my answer here is C. Now, before that, you can see my little formula came up here. If you're not confident with doing that kind of like logical thinking it out, how it all works, you can use this, right? When you come across questions like this, you can ask yourself, okay, if I make n larger, what will happen to the size of my margin of error, ZS over root n? If I make that n larger, what happens? If I make that n larger, that fraction, something over a larger number, that fraction gets smaller, right? If I make n smaller, that fraction gets larger. If I make my confidence interval larger, confidence level, so if I go from 95% confident to 99% confident, that Z value gets larger, which means that our interval gets larger as our confidence level increases. So you can play with that. You can use some dummy figures in questions like this, or you can sort of start to develop an intuitive understanding of how it all works. All right, celebrate. Next question. So here we are. Which of the following is a population parameter? Very fast question here. S. S refers to the standard deviation of the sample means. So it's not a population parameter, it's a sample parameter. Mu here, let's leave that alone because, spoiler alert, that's the correct answer. X bar here is the mean of the sample means. It's not a population parameter, it's a sample parameter. And Z is just the, Z score is the number of standard deviations that a particular value is from the population mean. So Z is not a population parameter. The answer is B, mu, which is the population mean. Pretty straightforward question. Celebrate. All right, here we are again. Not a lot of calculations to be done here. It says the mass of a particular variety of cake is claimed to be normally distributed with a mean of 660. That 660 value, that's the mean of the population. Okay, a random sample of 5 of these cakes is found to have a mean mass of 600. That is our mean from a sample that we've taken. That's going to be important. Which option represents an approximate confidence interval for mu based on this sample? Now, I can see straight away what the answer is, but let's just move a little more slowly. Take a look at our formula sheet here. The approximate confidence interval for mu is given by x bar, which is the sample mean, minus some numbers. And then the sample mean plus some numbers. That means that the middle value of our confidence interval is x bar, right? This is our confidence interval. The middle value is x bar. We subtract something from it. We add something to it. That's going to be our confidence interval. Now, x bar, a random sample of 5 of these cakes is found to have a mean mass of 600. The sample mass is 600. The middle value is going to be 600. Now, the middle value of this one's 660. This one's between 600 and 660. This one has the highest value of 600. The only one that has a middle value of 600 is B, and that is my answer. All right, so the thing to take away from here, the sample mean is between the upper and the lower values of your confidence interval. Pretty obvious from your formula, but this is also something that you shouldn't have to refer to a formula for. You should look at it and know sample mean 600. That's going to be in the middle, uppers and lowers. Celebrate. So a fun little question here. We've got some sort of motion of an object moving in a straight line, and we've got this. Velocity equals inverse cos 2x. That's interesting. This is what makes it a specialist maths question, right? Because we've got velocity, not in terms of time, but in terms of displacement. That's what makes it tricky. All right, so specialist, luckily we have a formula sheet and we have this right here, and we can go to work with this. Now, in particular, we can see that acceleration, and part A says determine acceleration with respect to x. We can see that acceleration is equal to a variety of different things, but the ones we're interested in, this one here or this one here. I'm going to use this one here, v dv dx. It's going to become obvious why I'm doing that. So let's just jump straight into it. Acceleration equals v dv dx. Now, the reason I like v dv dx for this question is because I know what v is. V is this right here. So not only do I know what v is, I shouldn't have too much trouble figuring out what dv dx is either. The reason is that v is this, and inverse cos formula sheet. All right, so the derivative of inverse cos, we've got a known way of going about that, right? So you can see the derivative of inverse cos x over a. Now, this isn't written in the form x over a, but I can write it in the form x over a relatively easily. So to get it in this nice form x over a, I've just said 2x is equal to x over 1/2. X divided by 1/2 is the same as 2x. All right, so now that I've got it in the form x over 1/2, I can just plug and play into my formula. So I know dv dx, let's use a blue pen here, dv dx is equal to -1 over root a squared. Now a, in this case, according to my formula, is 1/2, so a squared is 1/4, and then minus x squared. So now I know that v is equal to inverse cos 2x, and dv dx is equal to -1 over root 1/4 minus x squared. I can take all of that information and bring it over here now. So I can say that a is equal to v, which is equal to inverse cos 2x times dv dx times this. Now when I multiply that by this, I'll get all of this stuff on the bottom, root 1/4 minus x squared, but I'm also multiplying by this -1, so I get this one here. So determine the acceleration where a is this. The acceleration is right there. Negative cos inverse 2x over root 1/4 minus x squared. So that was part A. I can tick that, I can celebrate that, and we're going to jump into part B, which says use the result from 14a to determine a0 given all of this stuff here. Express your answer in simplest form. All right, so let's just sub in displacement 0 here. All right, so very quickly, I've put 0 in everywhere x was. Now, this simplifies, obviously, because we've got negative inverse cos, just a 0 there, and we've also got a 0 here, so we're going to end up with root 1/4 on the bottom here. Let me just tidy this up. All right, so that's a little neater. Let's keep going. We have acceleration of negative cos inverse 0. Okay, so what's that value there, cos inverse 0? Well, think about your cos curve. You can do this. The first time it's equal to 0, that's what our inverse is pi on 2. So there's our answer, pi on 2 on the top, but negative pi on 2. Negative pi on 2, and we're dividing it by the square root of 1/4. The square root of 1/4, some of us are not super comfortable with surds, so the square root of 1/4 is equal to the square root of 1 over the square root of 4, which is equal to 1 over 2, 1/2. So we're dividing by 1/2. So there's our answer, but we've got to get into simplest form. So dividing by 1/2 is the same as multiplying by 2. So negative pi on 2 times 2 is negative pi. Okay, need to double check here, negative pi, because it says use the result from 14a to determine a0, given that a0 is between 0 and negative 2 pi. Okay, yes, negative pi is an appropriate answer because it's between 0 and negative 2 pi. Now the units here, ms negative 2, done. There's my final answer. Now you might be wondering, hey, what if we checked this and it was wrong, like negative pi was outside of the domain? If negative pi was outside of the domain, we'd have to come up with a different value for inverse cos 0. Because remember, there are multiple values for inverse cos 0. We'd have to come up with some other value that spits out the correct, a value within this domain. But luckily, it's set up in a nice way. The very first solution for inverse cos does spit out a valid answer, negative pi. Good one. A nice, kind of question here, not too difficult. The slope field for this differential equation is given below, and then it says determine the value of the slope at point A. Now, this is point A, and if we look at the coordinates of point A, we can say that A is equal to -4, -2. Now, if we think in terms of coordinates, that's an x coordinate of -4 and a y coordinate of -2. That's good because it's asking us what the slope is. Now the slope you can see is negative, but we don't know exactly what it is. We can't just measure it, but we do have an equation that can tell us what it is. So all we need to do is sub in x equals -4 and y equals -2 into this equation here, and we'll know what the slope is because that's what it tells us. So dy dx equals -0.5, and then we're putting our y value in, which is -2, so -2, and then we've got a -4 on the end, and then we're dividing that by x, which is -4. Okay, this is -6, and then -1/2 multiplied by -6, so that's going to give me 3, and then 3 divided by -4, that's -3 on 4. That's my answer. Part A, done. That's all I needed. -3 on 4 is my answer. Celebrate that one. Okay, so what about part B? Use the slope field to sketch the solution curve for this, given that when x equals -6, y equals 3.5. Now, you need to embrace a certain level of inaccuracy here. You can't go for an exact correct answer. You just need to have a roundabouts, right? We're sketching this thing. So, x equals -6, y equals 3.5. We take that as our starting point. So I'm going to put our starting point on my curve here. Okay, here's my starting point, right there, right? Now, look, everywhere around that starting point, the slope is basically 0, almost 0, which means that my curve is going to have a slope basically flat, right? So it'll start here and then it'll come down just a little bit by the time we get here. And then look, the slopes are still pretty almost 0, not quite 0, sort of coming down a little bit though. Now, this is where the slopes are starting to get steeper downwards, right? So at the moment we've got like a slope like this, a slope like this, a slope maybe not quite like that, right? Still pretty flat, and then it's starting to pick up now. It's starting to get less, All right, now we're really in like serious slope territory. And then here we have undefined. Now that's going to be an asymptote. We even can be told it's an asymptote because x can't equal 0. So our curve is going to start trending down here. Getting closer and closer and closer to the y-axis, but never quite touching it. Right? Okay, that's not touching. Pretend that's not touching. All right, join these up. And there's my answer. Now, this is an asymptote. We can make it very, very clear that that's an asymptote just by putting in my little dotted line here all the way down to show that that's an asymptote. I'll just put some arrows on this thing. That's it. That's what we're expected to do. And you might be thinking, like, where are my marks? Because that was worth 2 marks. How am I getting marks for this? Well, you're getting marks because you came up with where it's supposed to start. That's where you're getting a mark from, and also showing that it's going to have a negative gradient in quadrant 2. And then you're also getting marks for showing that it has an asymptotic nature, and there's nothing happening in quadrants 1 and 4, right? It all is contained within quadrant 2 and quadrant 3. Done. Celebrate. So a fun little question here. We're talking about volumes of solids of revolution. The area between the graphs of these two functions is rotated about the y-axis to form a solid of revolution. Determine the volume. All right, now obviously I believe the first step to this should be drawing a picture. And it doesn't have to be the most pretty picture, but something like, okay, y equals 4x. I know what that looks like. It's a steep line like this, gradient 4 passing through the origin. And y equals 2x squared. I know what that looks like as well. It looks like a quadratic. All right, if I tidy this up a little bit, and if I extend the line, right, there must be some point at which they meet. Let me just change my scale a little bit, make it a little prettier. Beautiful. Now you can see my line's not as steep anymore. I've just sort of pushed the axes down, but it's a good idea to draw fast, and then if you've got to redraw again, redraw again. All right, we've got an area, and we're rotating that area around the y-axis. Now, in order for us to deal with this, I really start looking at it and I start thinking, what is that point? That point would be very, very useful. The question I'm asking is, at what point do these equations meet? And that's kind of going to be my first step. So I'll call it point A. Let's find point A. Y equals 4x, y equals 2x squared. If I just make those two equations equal each other, so 4x equals 2x squared, I'll be able to solve that. All right, so let's go move that one to the other side. So 2x squared minus 4x. I can see a common factor of x here. In fact, 2x is a common factor. So that gives me x minus 2 here. Something like that. Now, using the null factor law, x equals 0 or x equals 2. Perfect. Now we can disregard that x equals 0 because that's that point here where they're meeting. The point I'm interested in is this point here, 2. 2 what? Now if I sub 2 into one of these equations, doesn't matter what, y equals 4x, so let's do that. Y equals 4 times 2. So y equals 8. Perfect. I've drawn a picture. I know that they meet at 0.28. And now I just need to rotate these around the y-axis. So formula sheet, handy formulas here about the x-axis, about the y-axis. It's about the y-axis that we're interested in. So it's that second formula. Let's bring it up here and we'll start using that. Okay. Now for us to do this, we need to actually calculate two volumes. We need to calculate what happens when I rotate the quadratic around, right? And what's that area of the bowl? And then I'm going to calculate what happens when I rotate the line around. And then I'm going to subtract one from the other. And that's going to give me this piece in here. There are some tricks that we can use, but that's our basic idea. Now, because we're rotating around the y-axis, we don't want functions of x. We don't want y equals 4x, y equals something. We don't want y equals something. We want functions of y. We want x equals something. We want x equals something. So let's rearrange these. So my first one to rearrange is y equals 4x. That's easy enough. X is equal to y over 4. Easy. The next one, let's rearrange that one. So y equals 2x squared. Y over 2 equals x squared. And then square rooting that, I'll get x is equal to the square root of y over 2, plus minus. All right, now, how do I deal with the plus minus? Well, when I do this, I'm creating an inverse function. I'm taking the quadratic and moving it from there to there. I'm only interested in this top half, so I don't need the plus minus. I can just go with square root y on 2. All right, so I have this function, x equals y on 4. I have this function, x equals root y on 2. These are the two functions that I'm rotating around the y-axis. So I'm going to use that formula there. Let's do one at a time to begin with, and then I'll show you how to do both at once. The volume of, let's go with this one just being like A and this one being B. Okay, so the volume that's created when I rotate the line, this one, around the y-axis is going to be equal to pi. Terminals are important. Between 0 and you've got to be careful, not 2, because we're not rotating around the x-axis. 8, because we're rotating around the y-axis. So we're interested in this value right here, which is 8. Okay, and then we're taking our function and squaring it, y on 4 squared, with respect to y. Done. Okay, all right, and then we can move through there. We don't have a calculator, so we've got to do it by hand. So that's going to be the volume of A. What about the volume of B? Same deal again, pi. This time we're going between 0 and 8 again, right? Because that's our intersection point. We're rotating that around it. This time we're taking root y squared and squaring it. Well, I'm not even going to write that down because root y squared root y on 2 squared is just y on 2 with respect to y. Okay, so I have a volume, and that's going to be the volume of solid revolution of the line, and a volume, and that's going to be the volume of solid revolution of the quadratic. Should we proceed from here, or should I show you a cool trick? Okay, so if you want to proceed from here, you can. You calculate this, that'll give you a number. You calculate this, that'll give you a number. And you subtract one from the other, and you'll have an answer. The way that you can do this is to instead combine these into a single integral. How come we're allowed to do that? How come we can do that? Because we're still going between terminals 0 and 8 in both cases. We're multiplying by pi in both cases. Eventually we're going to subtract one from the other, right? Because we're going to do VA minus VB. Let me show you. We're eventually going to do VA minus VB. Or actually, we might do VB minus VA. I'm not sure, and I don't want to think about it. So I can get away with it by just sort of absolute valuing it. That way it doesn't matter what order I do the subtraction in. All right, so VA is all of this, and VB is all of that. So I can put all of that there, and I can put all of that there. So the volume is going to be equal to the absolute value of A and B. You can see they both have a common factor of pi, so we can bring pi out as a common factor of these two things, but they're also being integrated between the same terminals, 0 and 8, so we can just integrate them in a single shot. So we have a single integral now, pi out the front, pi times integrated between 0 and 8 of y on 4 squared minus y on 2. Now looking at this, it's been silly to keep it as y on 4 squared the entire time. That's just y squared over 16. Beautiful. Now that I've done that, I can do my integral. So v equals absolute value. I've got my pi here. All right, and the integral of y squared over 16 is y cubed over whatever 16 times 3 is, 48. And then minus y squared over 2 divided by 2. So that's y squared over 4. Okay, and we're going to be integrating that between 8 and 0 and an absolute value. All right, so we're just putting 8 in there, we're putting 0 in there, and we're done. Okay, so I'm halfway through. I've put 8 in so far, 8 cubed over 48 minus 8 squared over 4. And then if I put 0 in here and put 0 in here as well, I'm just going to end up with 0 cubed over 48 and 0 squared over 4. I'm just going to end up with 0. All right, so, and then an absolute value. So, final step, all I need to figure out is what 8 cubed over 48 is, no calculator, and 8 squared over 4, no calculator. All right, so continuing up here now. Now, I don't want to do 8 cubed. That's 8 times 8 times 8. That feels like too much work. But what I notice is that 48 has a factor of 8. So if I divide top and bottom by 8, I get 8 squared over whatever 48 divided by 8 is, which is 6. Okay, that feels more manageable. Now, 8 squared is 64, and 64 divided by 4 is 16. I feel like I can do that. So minus 16. Now, that's really all over here, because from here, what can we say? We've got the volume is equal to the absolute value of pi. Now, this is 8 squared, which is 64. 64 divided by 6. Let me just think about that for a second. 64 divided by 6, that's 32 over 3. So we'll go 32 over 3 minus 16. And then I see this 16, and I sort of want to get that into a single number, right? So what if I multiply 16 by 3? That's 48. So V is equal to the absolute value pi 32 over 3 minus 48 over 3. All right, and I think we're pretty much done here. We can finish this off. Now notice, we're going to end up with negative. So 32 minus 48 is negative 16. Negative 16 over 3. That's why we've got our absolute values here. My final answer is going to be volume equals 16 over 3 pi. And we can look for units here, just units cubed. Done. All right, so a little bit of work here. Now, like I said when I was doing this question, you can choose not to go down this path. You can instead do this value as a single integral, this yellow working. Do this as a single integral and then combine them at the end. Still absolute values, but combine them at the end rather than working them as a single integral. Maybe you'll find that more comfortable. Doesn't matter, but I've shown you one way to do it. This is how I do it. Celebrate. Done. So this was week 22. Going well. Awesome job. Next week we're back into Tech Active questions. Hope to see you then. Catch ya.